Hello everyone, in this lecture we will be going over 2016 USAJMO problem number 5. This is a geometry problem. Here's a view of this problem. Let ABC be an acute triangle where O is the circumcenter, point H is the foot of the perpendicular from vertex A all the way to the line BC. You can see point H here. Also, points P and Q are the feet of the perpendiculars from H onto the lines AB and AC. You can clearly see P and Q on my drawing. So given that AH squared equals 2AO squared, recall that AO is the circumradius. Prove that points O, P, and Q are collinear. So the way I will be proving this result, to show that OPQ are collinear, I will basically would like to show that, well, this is equivalent of saying that angle AQP is equal to angle angle AQO. But notice that we can further simplify this result because obviously points A, P, H, Q are concyclic, because you can see two supplementary angles here. Angle APH plus angle AQH is equal to 180 degrees. Let me write that down. Angle APH plus angle AQH is equal to 180 degrees. And notice further that angle ABH also notice that angle ABH is equal to angle AHP. Simple angle chasing will reveal that, obviously. For instance, because PHB is complementary to ABH, but PHB is also complementary to AHP, and that gives us this result. But further, because those 4 points, because quadrilateral APHQ is cyclic, AHP is equivalent to angle AQP. Therefore, this result, alternatively, we can show, instead of showing this, we claim it's easier to prove that angle AQO is equal to, so I will simply replace the AQP with ABH, angle ABH. So that's all we need to establish the desired collinearity given in the problem. So for instance, let's assume O is somewhere here. All we want, so that's our circumcenter. So we want to show that triangle, well, the angle ABH, so this angle here is equal to AQO, this angle up here. In fact, the way I will be showing this will be by further, I will prove something stronger. In fact, I will show that this triangle here, AOQ, I will show that this angle is actually a 90-degree angles. So I will show that triangle AOQ is similar to triangle AHB, so something stronger. So show triangle AOQ is similar to triangle AHB. And that's exactly what I will do in the next page. So in fact, let me just mention it here. So a couple of things first before I go further. I claim that this angle here, angle BAH, this angle is actually equal to this angle here, angle OAQ. And that's a simple consequence of the fact that the orthocenter and the circumcenter, so orthocenter is probably somewhere, oops, not like that, probably somewhere here. So here the orthocenter, let's call it H1. So H1 and O are isogonal conjugate points, and as a result, they are so these angles are equal, and we can actually very simply prove it. So let me just go ahead and prove it on this picture. So if I drop a perpendicular here, we know that because chord BC, so that's the midpoint of this chord, let's call it M sub A, and the midpoint of the arc BC, so here let's call it K here. So obviously, so this is a midpoint of the arc, as I said earlier, and MA is the midpoint of line segment BC. If I draw the angle bisector of vertex A, I know the angle bisector will hit that point K here, and notice the angles. Check that this angle here, angle HAK, is equal to this angle, angle AKO, and it is simply because these angles are alternate interior angles, because those two lines are parallel. AH is parallel to OK, and further because OA is equal to OK, because these are both radii of the circumcircle, so the circumradius, right? So therefore we have an isosceles triangle. Triangle AOK is an isosceles triangle, meaning angle AKO is equal to OAK. So that's also equal. So we have so AK is an angle bisector, and we have just proven that the two angles on both sides are simply equal, suggesting that the green angles here are also equal. So now that we have established the equality of these two angles, notice also that it's given in the problem that let's take the square root and then take the ratio of both sides. So we have AH over AO is equal to root 2. So we are also given the ratio of the sides AH and AO, and that's root 2. Therefore, all I need to establish this similarity here from side angle side similarity, all I need is is to show, in fact, so this reduces to showing that that AB over AQ is equal to root 2. So once we show this as well, so it shows that AB is root 2 times AQ, but also AH is given to be root 2 times AO. We know the angles between those two side lengths are equal. So as these pair of two side lengths are equal, as a result, those two triangles will be similar as claimed. So all I need to show in order to complete this proof is that AB over AQ is equal to root 2. So let me open a new page, and on that new page let's complete this using some trigonometric identities. So now notice that let's have a look at the inverse. So AQ over AB, that's simply equal to AQ over AH times AH over AB. So obviously notice that AQ over AH, AQ over AH, if you call this angle C here, that's also C simply. So therefore that would be simply a sine of C. AQ over AH would be simply sine of C. And in a similar way, AH over AB would be AH over AB would be simply the sine of this angle B. So therefore I can call this sine of angle ABH, if you will, or ABC, times the sine of angle angle C, ACB, angle ACB. so the product of these two signs. So that's exactly what we want to find. So now let's start with the following observation. Notice that I can represent the area of triangle ABC as 1/2 times BC times AH, the height, and notice that the height AH, as I said earlier, it's given in the problem that that's simply equal to √2 times AO, or you can, if you will, you can say √2 times R, where R is the circumradii, and moreover, we can also represent the area of triangle ABC alternatively as A times B times C over 4R. Notice that side length BC is simply equal to A, obviously. So now what I will do is I will cancel out some stuff. Obviously this 4 and 2 will cancel out. Ultimately this will lead to our first result, 2 times R squared times √2 is equal to B times C. So let's call this as 1. Now, second of all, we can apply law of sines on our triangle. So applying law of sines, in fact, applying the extended law of sines, I know that B over sine B is equal to C over sine C, which is equal to 2R. So therefore, this would imply that B times C is simply equal to 2R sine B times 2R sine C, or if you will, 4R squared sine B sine C, the product here. But then, so let's call this BC. So let's highlight this result as well, and let's call it 2. Now if I combine 1 and 2, so 1 and 2 will simply imply that well, obviously I can remove the BC's here, so I can make this side equal to the other side. The R squares will cancel out, and from here I will get that sine B times sine C is equal to 1 over √2. But then I can simply substitute this into this expression here. So therefore AQ over AB is equal to 1 over √2, suggesting therefore that AB over AQ itself, therefore let me put it down here on this corner, therefore AB over AQ is equal to √2 as desired. So therefore we have simply proven that that simply the triangle, so you can call this O now, so we have simply shown first that these two angles are equal, this angle and this angle here. Moreover, I can also see that the ratio of AB to AQ is √2, and it's also given in the as a condition in the problem that AH to AO is also √2. AH to AO is also √2, suggesting that those two triangles, let me highlight those triangles again. So this yellow triangle here is similar to this green triangle. But when that's the case, this suggests that that our angles, so that simply this angle B here is equal to this angle, so suggesting AQP. So AQO is equal to AQP, and that completes our proof. So hope you enjoyed the video. Looking forward to see you guys in our next lectures.